Hello and welcome back to the channel. I have a bit of a different video for you today on the topic of engineering rather than anything political or the normal topics that I cover, but I think it's pretty interesting, especially for people who aren't engineers. I've compiled a list of words and terms and phrases that engineers use frequently that other people who aren't in the industry might not have heard of or might be wondering what they mean. A lot of these words are actually not things that I learned at university, and when I first started at my first position as an engineer, I kind of got thrown into the deep end, having to learn a lot of new words, and it was a bit embarrassing not knowing any of these. But once you get accustomed to phrases like this that you use all the time at work, it's kind of hard to remember that other people might not know what you're talking about. So I don't know if it's engineers especially, but if you ever have to work with engineers, or if you're friends with engineers, then they might drop these words in just casually, expecting everyone to know what they mean. But if you're not working specifically in that industry, you might not know what they mean. And I hope I can prepare you a little bit for that experience by teaching you a few new words here. And there's a few principles behind these words that I think are just generally interesting. So without wasting any more time, I'll get right into the list. The first term I've got on my list is CAD, or Computer Aided Design. That's the name given to the computer software that engineers use to design physical systems, or to design a mechanical part. We used to use drawing boards and a good old pencil and a ruler, but these days it's a lot quicker and a lot more agile to use a computer and a keyboard and mouse to design things on a screen in 3D, and then use those 3D parts to make a 2D drawing after the fact. It's not just engineers who use CAD, it's also product designers, architects. If you've ever designed a kitchen at IKEA, they use CAD to design the layout of your kitchen, for instance. There's also 2D CAD, which is what a lot of PCB layout designers use to design PCBs. And I guess that should take us on to our next term, which is what is a PCB? I think most people these days know what a PCB is, but I thought I'd include it on the list anyway. It's a printed circuit board. To build any kind of electronic system, you need to make a circuit. But actually having wires and connectors all over the place is a very messy way of doing things. So the modern innovation that we use these days, the past few decades, these days you have a 2D board, and you get it printed to have the circuit, like a 2D circuit printed on the board itself. And you can find these PCBs in pretty much all electronics. So that you get big PCBs in your computer, you've got one in your phone, you've got one in your washing machine, probably in your kettle somewhere. And PCBs are usually covered in components and silicon chips and processors. These are all components that are usually these days surface mount, which means that after the circuit has been printed on the board, a big robot comes and places these surface mount components on the PCB, and they are soldered in place, which means to melt some solder, which is a kind of metal, metal alloy that is specifically designed to fuse metal together. So solder is used to stick these components to the PCB, and that can form a circuit. These days, most components are surface mount, just because it's a lot quicker and easier to put them on the PCB that way. But you still do get some through-hole components, which are sort of usually bigger components that have metal legs, and these metal legs stick through the PCB and are soldered usually on the reverse side. I know I'm going through these quickly, but I'm just trying to give you an overview, not an in-depth understanding. If any of these words do prompt a question, you can look it up yourself, or if you'd like me to go into more detail on any of these, please let me know in the comments and I will. Whilst we're talking about electronics, I'll mention my next word, which is AWG. This is American wire gauge, and it's the unit that we use to measure the gauge of a wire, or the surface area of the wire's core. So wires, of course, come in different thicknesses depending on what you're using them for. A thicker wire will be able to carry more current, more power, but thinner wires are usually used for carrying signals, carrying data. They don't need to have the huge gauge of a power cable, for instance. The funny thing about American wire gauge is that the higher the number, the thinner the cable. So a wire gauge that I frequently use in my job is 28 AWG, and that's probably the thinnest wire that I've ever used. I think maybe 32 is thinner than that, but you, for instance, in an Ethernet cable, which is a cable containing 8 wires, frequently what you see with those cables, you probably have one in your home if you have a internet connection, and if you don't have an internet connection, I don't know how you're watching this, but in an Ethernet cable that carries network information, sometimes for internet usage, you have 8 of these wires inside the cable that are all 28 AWG. That's a very thin wire, but something like a 10 AWG, which is probably the thickest wire that I've ever had to use, is that's very thick. That's for carrying power usually. And this might be a good time to point out that we often talk about electricity as in terms of current and power. Voltage is usually determined by the power source. If you're using a battery or whether you're plugging it into the wall, the voltage is you need to know what voltage you're using, but that's more of it's a case of needing to adhere to that standard. So if you're on a 12-volt power supply, that's something that you need to know, but the actual current that you're using is something that's what you're designing the system for, if that makes sense. So you have to know the voltage of what you're using. Everything will be designed for that voltage, but using that voltage, you can change the amount of power you're using by changing the current that's being drawn through the cables, through the wires. If you want to know which wire gauge to use, the first question that's asked is always, what's the current rating? That's what you need to know to know what kind of wire you need. The voltage, in that sense, is kind of secondary. It's not very important, although of course it's important for other things. Staying on the subject of electronics, you've probably already heard of hardware and software, but I'll go over that quickly anyway. Hardware is the word that we use to describe physical things. So for instance, the hardware in your phone will include the screen, the connectors, the camera, the battery. Those are all hardware. But the software in your phone will be the information that you're seeing, almost the operating system on your phone, whether it's Android or it's iOS or a Windows phone. On your computer, of course, Windows might be the software you're using if you don't have a Mac or Linux. The software is everything that you are seeing on the screen and interacting with, and the hardware is usually what you're using to interact with the software. So you take a picture using the camera on your phone, but the processing that goes on with that image is all software. The word that less people know is firmware, which it's called firm because it's halfway between hard and soft. And firmware is the sort of the software that's going on in the background that's relating to your hardware. So if you think about something like a toaster, it's not something that you would typically think of as having software. Your toaster probably has something more like firmware. So when you push down the plunger on your toaster, what goes on? Okay, well, it depends on the setting that you set it to, and based on that, it will turn on the heat, and it will then turn off the heat and release the spring that makes the bread come back up. Those are all things that happen according to the firmware in your toaster. Even much more complicated electrical systems also has firmware, as well as having software. The tricky thing about firmware is that you really aren't interacting with it. So if something goes wrong with the firmware in your computer or in your washing machine, you really can't tell because it'll have a hard time telling you that that's what's wrong with it. And even if you know what's wrong with it, it's probably quite difficult to fix it yourself. Coming back to mechanical design, I want to take a minute to talk about screws and about all kinds of fasteners, because these are all everyone knows what a screw is and probably knows what a nut and a washer is, but there's all different kinds of screws, and they're all it's not that difficult to learn, but it's something that I had to pick up very quickly after I left university. I knew very little about screws and different screw standards, but that is pretty crucial for being a product design engineer, probably whether you're working in electronic or mechanical design. The most common kind of screw that I use are metric machined screws. You'll know if you're working with a machined screw because the tip of the screw will be flat. It won't hurt if you poke it against your finger, for instance, and the actual thread of it is quite fine. The thread is the groove that has been cut into the shaft of the screw. The cut is quite shallow and the cuts are all very close together. Machine screws can come in metric or imperial. I, working in the UK, almost always use metric, but there have been a few occasions where I've worked with a system that is already imperial, and then therefore I've had to use screws to fit with that system. The imperial standard is called UNC, and I can't remember what that stands for now, but metric screws are all called M and a number. So the diameter and the thread of the screw are determined by that M number. So the typical screw that I'll use, my favorite screw standard, is M3. If you're a product designer and you design with screws, tell me your favorite screw standard. But M3 is it's a quite small screw that we use in a lot of electronics, and the diameter of the shaft is 3 millimeters. So an M3 screw will fit quite comfortably through a 3 millimeter hole. And any M3 screw will fit with an M3 nut. That's not quite true actually, because there are a few different thread pitches that are associated with each standard, but there's one of those thread pitches which is far more common than the others. So for all intents and purposes, an M3 screw will fit with an M3 nut, and you can happily design according to that. When I say the pitch, I mean the distance between the cuts, the thread. So your metric machine screws will be M3, M4, M5, and then once you get to M6, you stop getting odd numbers, so it only goes to M8, M10, M12 after that. I don't know what happens when you get really high. Maybe they start skipping even more numbers, but I'm just telling you this because you'll look a little bit silly if you ask if you ever have to ask anyone for an M7 screw, they'll probably look a little bit funnily at you. I don't know if they literally don't exist, but it's definitely not a common standard. So for the smaller sizes, it's every single millimeter. You get a new one, M3, M4, M5, and you even below a certain amount, you get half sizes. So you get 2.5 or 2. As well as fitting into nuts, you can also what I do often when I'm designing a metal part is you can ask the machinist to cut a thread straight into the metal, so the screw will just go right into there. You don't need to design it with a nut in mind. And having a standard, whether it's metric or imperial, just makes things very easy for designing a system. You just have to stick to one standard, and if everything in your product is M3, then all the screws will fit in all the holes, and you can quite happily just buy off the shelf M3 nuts that will fit with M3 screws from a different supplier. They're all part of the same standard. It's a very common standard, so you should be able to find plenty of parts to fit with it. The other main kind of screw that you can get is a self-tapping screw or a thread-forming screw. This is not a screw that's meant to fit with a nut. It's a screw that goes directly into a material, and that material can be plastic or wood or even metal if you have a really sharp, very tough screw. You know if you're working with a self-tapping screw because the end of it will be usually quite pointy. It'll have a sharp tip that you can, it'll hurt if you push it into your finger, and the thread on it will be, the pitch will be a lot bigger and the thread will be a lot coarser. And it's designed that way so that as you screw into the plastic or wood or whatever, or plaster, it'll cut the material as it goes. The standard that determines those sizes is a little bit mysterious to me. If you go to somewhere like Virgin's or Homebase, you'll often see something like a number 6 or a number 4 or a number 2 screw. Again, those sizes are going the bigger the number, the bigger the screw. So a number 6 screw is quite that's the kind of screw that you'd buy to, you know, screw your home appliances into some brickwork or into plaster. Because self-tapping screws don't have to fit with any other parts, they just need to go into, you know, a block of material. That I believe the standards are a lot less. So you basically just need to find a screw that looks about right for your application, and that's something that I suppose you get just from experience. The only other thing I have to say about self-tapping screws is that you sometimes, but not always, need to drill a pilot hole to into the material before the screw goes in. So a pilot hole is a hole that you drill in the material that is smaller than the maximum diameter of the screw. So it just helps the screw to go in, especially in a hard material like metal. You'll definitely need a pilot hole. In a soft material, you might need to drill any hole at all. That pointy end of the screw will go straight into the wood or the plastic, and it'll make its own hole and push the material out of the way as it's forming its thread. I don't know why it's called a pilot hole, but it's not a bad name for it, I suppose. And I suppose it helps to guide the screw. I don't know why that relates to being a pilot. Before we get off the topic of screws, I still have more to tell you about the head of the screw this time. The head of a screw can be either countersunk or it can be a number of other head shapes. But the main thing you need to know about a screw is whether it's countersunk or not, because a countersunk screw will not fit into a regular hole, and a regular screw will not fit into a countersunk hole. And what is countersinking? It's where the head of the screw has a kind of conical shape, so that the top of the screw will become flush with the surface that you're screwing onto. So you only be able to see the top surface of the screw head, and there won't be any bump left by the screw. It'll go straight into this well that the countersunk hole will have this kind of well that the screw will go into and sort of almost disappear. Whereas a button head or a pan head or a cap head, those will all stick out over the surface unless there's a counter bore. That's the other thing you can do. A counter bore is a well shape with straight edges, not a funnel shape, but straight edge hole that can help you hide a cap head screw or a pan head or a button head. When you get up to bigger screws, which are sometimes called bolts, you might get a hex head, which is a screw that has no drive at all. It just has a hex shape, kind of like a bolt, where you can screw that in with a spanner or a wrench, as Americans call it. But speaking of drive, the drive of a screw is the shape of the shape of the indentation in the screw needs to match the shape of the screwdriver, so that you can not just get the screwdriver into the screw, but actually get a good torque around it. So there's always a compromise between how common the screwdriver type will be and how good the torque will be usually. So on one end of that, you have the flathead screwdriver, which you've probably seen before. The head of the screwdriver just looks like that, and the screw just has a slot that the flathead screwdriver will sort of go into the slot, and you'll be able to drive the screw. But if you've ever had to work with those, you'll know that the screwdriver often slips out because there's just nothing stopping it. So it's quite annoying, especially at high torques or at high speed. The screwdriver will just sort of slip out when you're trying to screw it. So the next one up from that is a Phillips drive or a posi drive. This is the other kind of screwdriver you're probably familiar with, the cross shape on the head and a little cross shape on the screw, which comes out less. But still, if you don't have quite the right size of screwdriver, it might not go in, or it might still slip out. One up from that would be a Torx drive, which is also called a hexalobular, which is the non-brand specific version of that name. It means the same thing though. A Torx drive is a 6-pointed star that is it's very good for keeping the screwdriver in the screw head. It won't slip out no matter how much torque you put on it, pretty much. but it's not very common. And the thing with a Torx drive is that you need to have exactly the right size of Torx driver to go with that Torx screw. So each screw standard, M3, M4, whatever, will have a slightly different size of Torx drive, and you'll need a different screwdriver or a different screwdriver head for each of those sizes. As long as you have the right screwdriver, it makes it really easy. Similar to the Torx is the cap head screws, which often have a hex-shaped indentation, or a socket drive, as it's sometimes called. It's just a hexagon shape, and you can, if you've ever bought anything from IKEA, you'll be familiar with this, with the Allen key that's often supplied with the IKEA furniture to put it together. An Allen key is just it's a really cheap way of making a screwdriver. It's just a hexagon shape that's been extruded and then bent around a corner. But again, you need the exact right size of Allen key to fit with that size of socket in the head. And the last kind of drive I want to talk about is a security drive, which is usually it's a Torx type of screw with a pin in the middle. So inside the star, there's a pin sticking out that makes it so you can't use a normal Torx screwdriver on it. You have to get a special Torx security drive with a hole in the center of the screwdriver that will go with that pin, and it'll fit in the screw. And that basically makes sure that if you're installing a product in public or in a place where you're worried that people will be able to get at it, someone who's trying to take that thing apart probably won't have that kind of screwdriver in that exact right size to be able to get that thing apart. So without actually having to lock your product, you've ensured that it's at least quite inconvenient to open it or to get those screws out. Gosh, that was a lot about screws, wasn't it? That's all I've got about screws. It's something I could probably talk about for ages. Another standard that gets talked about a lot in product design is the Ingress protection standard, or usually shortened to IP. You'll often hear a lot of consumers are becoming aware these days of the IP standard. You may have heard of IP66 or IP67 or IP68, and those are all different Ingress protection standards that guarantee your product will be water resistant usually. But what a lot of people don't know is that it's only the second number that determines the protection to water ingress. The first number is against physical particles and physical ingress. So to be completely accurate, you wouldn't call it 67 or 68, although we often do say that. You would call it 67 or 68, because it's not, those digits don't form a number. Those are two separate digits. One of them defines the size of particle that can get into the system. So the 6 in IP67 refers to a very fine talcum powder kind of dust. And a product that is rated for IP6, IP6X, will need to be tested against, but having a bunch of dust blasted at it, basically, to see if the dust will get in. If you have a camera, then you are probably concerned about sand getting in if you ever take pictures at the beach. That sort of thing. Sand is a slightly larger particle than dust, so that would be probably IP5X, to protection against sand. And then right at the bottom end, if you're looking at like an IP1, would be, is there a hole big enough to get a finger into or to get a spanner into? Coming onto that second digit that a lot of people do know about, because it's basically how waterproof a product is. At a certain stage, of course, when you're protecting against water, you're probably not going to have any really big holes in your system. So that's why we talk about 67 or 68, because the dust prevention is kind of assumed to be guaranteed. If your system is waterproof against 1 meter of submersion underwater for 30 minutes, there's probably not going to be sand and dust getting in there. Each of the numbers in that second digit refers to a different test that the product has to pass. So X6 or 66 is being blasted by high pressure water. 65, the one before that, is being kind of sprayed in something kind of like rainfall. So it's the water's not at a high pressure, it's kind of being drizzled on by in every direction. Like I said, 66 is a high pressure water that can sort of push past a lot of seals that you might put on a product. 67 is immersion in, I think it's 1 meter of water for 30 minutes. And 68, a lot of people will rate their product as 68 without explicitly specifying what it is. It's a little bit of a contentious topic. The most common accepted definition of 68 is 1.5 meters for 30 minutes. So it's just the same as 67, but a bit deeper. But 68 really refers to whatever test you want to put it under that is more than 67 or 66. The thing about IP standards is that, as I said before, consumers are starting to be aware of it, to the point that now having IP 68 on your product has become a kind of prestige symbol. It's something that consumers will recognize as a good thing. They'll be looking for that on the product. So whether it actually needs to have that level of protection from submersion or not, people kind of expect it these days. So a lot of manufacturers are kind of pushing, a lot of product designers, companies that design products are pushing their designers to design the products to IP68, just so they can say that it's IP68 on the box or on the Amazon description page, even if the product is never actually going to be submerged, or if they probably don't even care about what the 68 precisely means. It's just a kind of status symbol. And that's all the words I have written down today. This video ended up being a lot longer than I thought, so maybe I'll take some of them out. If I think of any more, I might do a part 2 for this video, but only if I see some people who are actually interested in this. This kind of stuff I think is interesting. I don't know if other people find it interesting, so please let me know what you thought of that. Did you know all of these words? If you do, then if you knew all of them already, then good for you, and let me know. If you learned something today, then I'm pleased I was able to teach you something, and I hope it was interesting. Either way, thank you very much for watching, and I will see you again soon with probably a more normal type of video talking about politics or something. Leave your comments below as always, and I will read all of those, and I hope to see you again soon.